We are going to go over the notes for simple harmonic motion, and we need to go through some vocabulary before we get into the formulas. So when we say that an object has periodic motion, we mean that it occurs in intervals. So it repeats its motion like a pendulum swinging back and forth. The oscillation is the actual movement of that back and forth motion. And these happen at regular speeds or steady speeds. Every simple harmonic motion is going to experience a restoring force, and this is the force that directs an object back to that equilibrium position. And that equilibrium position is the middle. So if we have a pendulum, it's that center point as it goes back and forth. It's that straight downward motion. This is like water in a pond. If you throw a rock in to a pond that has a steady surface, eventually those ripples are going to steady out. And gravity is acting as the restoring force to return the water back to its equilibrium position. The amplitude in simple harmonic motion is going to be the maximum position from equilibrium during an oscillation. So how far does the pendulum swing up? Now a cycle is one complete oscillation, so it starts and ends at the same point. It's a repetitive motion. Make sure I spell that right. And then we define simple harmonic motion as an oscillatory motion under a restoring force proportional to the displacement from equilibrium position. That's our official definition. So there's two basic types of simple harmonic motion that we're going to deal with. We're going to deal with springs, and then we're going to also deal with pendulums. We're going to start with springs, and we got to discuss a few things about springs that we've learned earlier in the year. So if we remember, Hooke's law was used to find the force that was applied to the spring at any point within the stretch or the compression. So if we remember, that is F equals Kx, where F is the force measured in newtons, K is the spring constant measured in Newton per meter, and X is the position from equilibrium, and that's measured in meters. And remember that this formula had a negative in it that showed that it was a directional force. So we put our directions in negatives and positives, and so we can decide that on our own rather than relying on the equation to do it as well. And this is also a review work done by a spring. So if we want to know the energy that's being used within our simple harmonic motion, if we remember, work equals the change in energy, and as a spring is compressed, we're changing the potential spring energy. And anytime we have our triangle, that's final minus initial, so 1/2 kx squared, that would be the final position, minus 1/2 kx naught squared. So here's our spring potential energy, and so we're just taking the final minus the initial. So W is going to be work, measured in joules. K is going to be the spring constant, again, measured in newtons per meter. X1 or X0 is going to be the initial position, measured in meters. And then X2 or X final will be the final position, or second position, measured in meters. So then we have our example. A 4 kilogram mass is suspended from a spring and produces a displacement of 20 centimeters. What is the spring constant? So here we have our spring, and we have a mass from it, and it's 4 kilogram. And this 20 centimeters is going to be our x, and we want to convert that to meters. And we're looking for what is our k value. Okay, so the force that's being applied to the spring is going to be the weight of the block, which is mg. And we also know that the force of the spring is kx. So if we take these two parts and set them equal to each other, we get mg equals kx. And from here, we can solve for k. So rearranging the formula, we get k equals mg over x. And now we can plug everything in and solve. So 4g is 9.8, and the distance from our equilibrium was 0.2. And when we plug that into the calculator, we get 196 newtons per meter. And there's our answer. So the second part of this question says the mass is now stretched and held a distance of 8 centimeters. What is its potential energy? So now wherever that 4 kilograms was, that's its new equilibrium point. So now we have a change in x of 0.8 or 0.08 meters. Okay, and we know our k value because we just solved for that. And we want to know what is its new energy. And the mass that's hanging off of it is that 4 kilograms. So our formula for spring potential is 1/2 kx squared, so you can tell we don't need the mass. And US equals 1/2 times 196 times 0.08 squared. Okay, so when we plug this into our calculator, we have 0.5 times 196 times 0.08 squared is going to give us an energy of 0.627 joules. And you want about 3 numbers, and always round to that third number. So let's discuss simple harmonic motion. And one of the main ways that we can illustrate simple harmonic motion is a mass that's oscillating back and forth on a spring. So here we have our equilibrium position. Okay, so that's x equals 0, and it's going to go back and forth. So if it starts here and we pull it out here, then it's going to go back and forth, and it's going to swing around like so until it returns back. So that's one complete oscillation. It started, then it went through the equilibrium point, swung back around, and then came back to its original position. So that's the actual path that it's taking, that the mass or the block is taking. the A is going to be the amplitude of our simple harmonic motion. So capital A is for amplitude, and that's the farthest that the block goes as it swings away from the equilibrium position. And it'll repeat itself, and it'll swing back and forth forever, as long as we don't have any resistive forces like friction, or something changing and altering its positions. Okay, so we have negative and positive that's showing us our direction, just like on our number line. Okay, and the first thing that we want to look at is the restoring force, the force that's taking place on our box. Okay, so this is the restoring force. And if we have a negative force, then that means that the box is in a positive position. And if we have a positive force, then that means that the box is in negative position. So if the force is being applied this direction, then it must be over here because it's pulling it back towards equilibrium. Remember that the restoring force always pulls back towards equilibrium. And just as a reminder, we have our force in newtons. M in any of our equations is going to be mass. Again, that's in kilograms as our standard. A is going to be our acceleration. Okay. And our formula, general formula, is this one here, which is what we were just using in the previous two problems as well. Hooke's law, and then our regular Newton's second law. So if our acceleration is positive, that means it's in the positive direction, so to the right, then the block must be moving in the negative x direction. If the acceleration is negative, then the block must be moving in the positive x direction. So acceleration, we have to compare to velocity. And so if we add up here to our diagram, this is going to be negative acceleration. This is going to be positive acceleration, just as far as our directions, positive and negatives go. So as the block is moving to the right, it's going to be slowing down. And so if our velocity is to the right and positive acceleration, we have to look at our path. So during this first path, we're going to have positive velocity because it's traveling to the right. Over here we have negative velocity because it's to the left, as well as here. And then we have positive velocity again over here. And so we have to look up where in our diagram is it speeding up and slowing down, and how does that relate to our positive acceleration. So remember that when we have the same sign, we should be speeding up, and different signs we should be slowing down. So during this segment, when it's moving in a positive direction, we're slowing down, so this segment has a negative acceleration, and that's as it's moving in a positive direction. So negative acceleration, positive direction. Here we're moving in a negative direction and we're speeding up, and then we start slowing down again, and so that correlates over here. So this is just a general rule that if we're in a positive position, we're going to have a negative acceleration. If we're in a negative position, we have a positive acceleration. And acceleration is going to be at its maximum at the amplitude. So when x is at A and negative A. It will be 0 when it's at x equals 0. So acceleration is at its max at the extreme because it has to change directions 100%. Okay, then we have K, which is our spring constant again. Measured in Newton meters. our velocity, so reminder for our directions, positive velocity is to the right, negative velocity is to the left, and its max will be when x is at 0. Okay, right here in the center. It's going to reach 0 when it's at the ends. So this is opposite of your acceleration. And then your x for our directions, negative x is to the left, positive x is to the right. And just a reminder that max displacement is at A and negative A. So our amplitudes are going to be our max displacement. So let's work through two quick problems. General setups for our simple harmonic motion. Okay, we have a 2 kilogram mass that hangs at the end of a spring, so it's hanging. So here we have mass, we have our spring, and then we have mass. Okay, so a mass, 2 kilogram mass hangs at the spring, and we know our spring constant, and it is displaced 12 centimeters and released. So this mass is pulled downward, pulls down 12 centimeters, and then it bounces up and down. And what is the acceleration at the instant the displacement is 7 centimeters? So this is going to be our amplitude, because that's how far it pulls down. And we want to know what is the acceleration at x equals 7 centimeters, or 0.07 meters. So this 0.12 we're not actually going to be using at all. Based on our formula that we used up here, we know that our restoring force equals the force on the spring, so Kx equals ma, and we are looking for our acceleration, so we rearrange our formula and we can plug in and solve. We want to make sure that we use the proper x, and we get that from reading our question carefully. And so when we calculate that out, we end up with an acceleration that is 14 meters per second squared. So for example 4, it asks what is the maximum acceleration, so we're looking for acceleration, for the 2 kilogram mass in the previous problem. And so we want to think about where does that maximum acceleration occur. And maximum acceleration occurs at the amplitudes. So here we're going to use that 12 centimeters, or 0.12 meters. And we still have the same K value. And we're still using the same 2 kilogram mass. So using that same formula that we just used, ma equals kx, we can look for the maximum acceleration, which is at its amplitude. And you've got to make that connection that maximum acceleration always happens at the amplitude. And so when we calculate that out, we end up getting 24 meters per second squared. Okay, so everything we talked about previously had to do with position, velocity, and acceleration, and where it was. Now we want to talk about how long these oscillations occur. So here's our period and sinusoidal nature of SHM. And the sinusoidal is talking about the actual graph, which we'll get into a little bit later, but we're going to use a little bit of trig as we talk about some of these things. Okay, so with a general SHM. So this works for any type of simple harmonic motion. We've talked about springs and pendulums, and we're going to go into that general, or we'll go into those specifics later on. But this is just general formulas for the period of any object in simple harmonic motion. And so to calculate the period, it's going to be 2 pi times the square root of the negative x divided by a. Okay, so the reason why we have these as opposites in signs, or opposite signs, is because remember that the x and the a were always opposite signs in our original diagram. And so in order to take the square root, we have to have the opposite of one of them, or take the negative of one of them. So pi is going to be your standard 3.14, and then t is going to be the period. So that's how long does it take for one oscillation. A is still acceleration, measured in meters per second squared, and x is position, measured in meters. So that's our general formula. And if we look specifically at a mass spring oscillator, we're going to take this formula and we're going to modify it to be specific to a spring. And that's the key thing here. We're going to look at a spring and we're going to look at a pendulum tomorrow. So we want to make sure that we're keeping each of these straight. And these period formulas are on your AP reference chart. So the period of the spring, S for spring, and then for pendulum we'll put a P there, is going to be 2 pi, and then the square root of the mass divided by the spring constant. So this will be period of a spring oscillator. Again, still in seconds. M is going to be the mass, and this will be the mass of whatever's on the end of the spring. And then K is going to be our spring constant, newtons per meters. And then we have angular frequency, and we use angular frequency because we're talking about a repetitive motion, and circular motion can be, and often is, simple harmonic motion. So we use angular frequency in this one scenario. And so angular frequency is going to be K divided by M. So nothing really new, but we of course need to make sure that we're using it. So angular frequency is a regular frequency, so we can use hertz or we can use seconds to the -1. And remember, those are the same thing. We learned that in the previous unit. And then K is, again, our spring constant. You see that pop up a lot because we're talking about springs. And then M is the mass again. Now, to find the position at any point or at any time during an oscillation, we're going to use this formula. And I don't necessarily want you to be so concerned with this formula. This is just it's a specific way that we can find position. And more, I want you to know that this segment here is going to be how we calculate angular frequency as well. So we can write this two different ways. So at any given time, if we know the frequency of our simple harmonic motion and the amplitude, we can figure out where the position of our mass is going to be. So x is going to be the position, and that's at any given time. So let's say that we're 10 minutes into our oscillation, we can figure out where the mass is going to be. A is amplitude, also measured in meters. F is going to be the frequency, and W is going to be our angular frequency. And so those two things equal each other. I'm going to go ahead and circle that so that way you can see. Okay. So same formula there. and then t is going to be just the general time. Notice this is a lowercase t, and then up here we have a capital T. Capital T is the period, so that's one oscillation, and t is just some period of time. Okay, so a frictionless system shown below has a 2 kilogram mass attached to the spring, and it's actually not shown below, sorry about that. And we know that we have our spring constant, and the mass is displaced a distance of 20 centimeters to the right. What is the frequency of the motion? So, write out our knowns and unknowns. We know the mass, we know our spring constant, we know our maximum displacement, and just a reminder, we want to convert that to meters. And we want to know what is the frequency. Now remember that frequency and period are inversely related. And so we can take our formula and flip it over or inverse it or solve for period and then inverse, however you would like to solve it. So we're going to find the period of the spring using the formula we just wrote. And then plug in. And when we find our period, we get 0.444 seconds. And then to find the frequency, we want to take the inverse of that. So on your calculator, the easiest way to do this is with the answer button. So if we type this in, so I can show you here, you have your 2 pi, and then you're taking the square root of 2 divided by 400. That gives us our 0.44. And we want to take the inverse of that. So you're going to do second answer, and then you're going to use this -1 right here. This is the inverse. It makes it super easy. And when we do that, we get our frequency, which is 2.25. The unit for that is seconds to the -1 or hertz, whichever one you choose.